Okay, so for those of you who don't know me, I'm Philippa. I'm just coming to the end of secondary PhD at the moment, and I'm looking at manipulations of object-based audio to improve speech intelligibility. So I am sponsored via the SRA project from the EPSRC, so thank you to them for funding. And then also, because this is a talk in two halves today, I'm also presenting some research I did before I came to Salford, actually from 4 years ago, so you have to excuse me if I forget anything. And that was at Boise State University in the US in Idaho, and that was funded by the NSF, so thank you to them. Like I said, it's going to be a tale of two acoustic elves today, so I'm presenting a little bit of psychoacoustics and a little bit of environmental acoustics as well. If there's anything, I don't know, you've all kind of done both sides, I'm guessing, but I'll kind of just cover them anyway, just in case, and just for the benefit of the video recording as well, if that's all right. If you're on Twitter, by the way, my handle is this. And if you want to tweet if you're team psychoacoustics or team enviro-acoustics, have a little competition, just for fun. Okay, so what am I actually going to be presenting today? So the bit from Salford is the psychoacoustics bit, and this is a listening experiment that I conducted early this year, looking into background music and the effects of percussiveness and tempo of background music on speech intelligibility. And then the part two is the bit that I did in the US, techniques on Volcano and geyser monitoring to track Santa sleigh, and whether or not it's an actual method we can use is another matter, but I thought it'd be fun to do it anyway. So the psychoacoustics bit, and like I said, just for the benefit of the people watching on video, so what is speech intelligibility? What I'm looking at then is these kind of bottom-up and top-down processes. So bottom-up, hearing through the ears, and the top-down bit is where the mind is kicking in and there's like thought process going on. So that's the speech intelligibility bit. It's to do with the amount of speech that you understand from the signal that's sent to you, I guess. So there's a difference between audibility and intelligibility. So you can have a really audible signal, but it might not be intelligible if, for example, you're listening to something in your second language. Or conversely, you could have something that sounds terrible, but it can still be highly intelligible if you have other semantic cues, such as visual cues. And then you also have quality versus intelligibility. So you can have something that is highly intelligible in terms of speech, but it might not be accepted by the speaker for whatever reason. So it could be they don't like something, or they perceive it as being too loud, or the quality as being too bad. And then the background then to where I'm coming in. So the BBC did a vision survey in 2010, and Lauren also did a survey earlier this year as well, looking into issues to do with speech intelligibility and broadcast audio. One of the main complaints, or one of the four biggest complaints they received about is background music. But the complaints are for various different reasons. It's not one particular reason, so it's kind of compounded. So it could be the perceived loudness. So in other words, people feel that the music is too loud compared to the speech, or when the music kicks in, there's like a big jump in the perceived loudness. It could be to do with audibility. So again, that level difference, the signal to noise ratio. It could be people feeling like their emotions being manipulated. So for example, when there was a program on Radio 3 about Grenfell Tower, and the producer wanted to insert spaces in kind of thinking and kind of reflecting about the program, and so they put these sustained piano chords in, and there were lots of complaints because people felt that their emotions were being manipulated by that program and by the music. And then there's also expectation as well, so things like Kraftwerk music being used on a BBC Radio 3 program, it's kind of unexpected and it's a bit jarring for people, they don't like it. Or likewise, there was a program, I think it was like a history of art program on TV recently, where they used prog rock music, and everyone's like, "Oh my god, it's horrendous." So actually, all they did was to turn it down a bit, and people got used to it, and it was fine. So the causes of this, you can kind of categorize them into three different categories. So you've got your energetic masking, which is kind of your level differences and frequencies of the material as well, if that's crossing over. It's going to cause energetic masking. There's informational masking, which is a bit more hand-wavy, where, for example, you've got like two competing speakers, for example, that would be informational masking. So it's not completely masking the signal as such, but you've got some kind of distraction going on that's pulling your attention away from the main speaker. And then obviously taste and culture as well. So that goes back to the thing about the program with rock music being used. And the BBC have two directives regarding background music. So they've said, first of all, try toning the music down by 4 dB after you've mixed it and see if that makes a difference. And generally that kind of sorts most things out. But then the other directive they've got is to avoid music with lyrics and under speech, and music with heavy percussive beats. But they haven't really specified what they mean by heavy percussive beats. Is that to do with timbre, in other words, the instrumentation that's being used, like drums? Is that to do with the rhythm that's being used? Is that to do with the attack on the instrument? They haven't really said. And when they did the survey, they didn't really do that much else. They did some experiments, but apparently like the results were messy. They haven't published anything, so nobody really knows what happened. And as far as I can make out from the people I've spoken, they didn't do anything on speech intelligibility as such. So it was more quality ratings and people's preferences. As part of my PhD, my PhD incidentally is in several segments, and this is one of the segments. And like I was saying, what do the BBC mean by percussive beats and what's been previously tested? Well, apart from the BBC Vision survey, most of the other tests have been to do with hearing aid technology, for example. So you might have one setting for speech and one for music, but they haven't really tested the two together, for example. Or they might have looked at, again, just the quality or preferences for people, but they haven't looked specifically at speech intelligibility for background music when you also have speech involved as well. So the test I did earlier this year was looking at this percussiveness and tempo, and we looked at tempo because there's been some studies to do with this neural entrainment as well, but again, not necessarily to do with speech intelligibility, so I thought it would be an interesting thing just to put into the mix. And so these are my null hypotheses. In other words, I apply something, there's no change. And I tested this both objectively and subjectively. So we were using Yan's glimpse proportion model to look at the energetic masking. And the way I set up the experiment was so that the energetic masking of all the masker and speech pairs would be the same. So in other words, the energetic masking I kind of forget about because that's not what I'm interested in. I'm more interested in the informational masking. And so that's how I set up my speech and noise test. In other words, you play sentences in noise, you get people to listen out for a target word in each sentence, and then you compare the word that they've heard versus what you've actually played them and give a correct word score, which equates to speech intelligibility. So my conditions, I had 4 pieces of music then. And this was a bit of a tricky thing because as you'll see, I'm also looking at tempo, and as soon as you down tempo a regular WAV file, it just distorts everything. It sounds horrible. So then I was looking at MIDI files, but when you assign MIDI files to some kind of synth instrumentation, it just sounds a bit false. And then I was looking at commissioning somebody who leads a string quartet, and he was going to very kindly tag me onto the end of a session to record some music for me at different tempi, but then my supervisors decided don't do that because each time a string quartet records something, it's going to be slightly different each time, and we want consistency for this listening test. So I ended up using Apple loops from GarageBand in the end, putting something together myself. And that kind of works because it has this wrapper around it, so you can basically down tempo it and it doesn't really distort it. So I'm sorry, I should just explain as well about that music. So I had a string quartet playing legato style. I had the solo cello playing, I guess, with a bit more attack. M3 was the same solo cello, but with lightly percussive accompaniments, so things like the Sfinga marimba and kind of shakers, maracas. And then M4 was my heavily percussive in terms of it had drums in it, had like 2 arpeggiators on it, had that cello in it and bass and all sorts of other stuff going on. So like just threw everything in, thinking that would have an effect on speech intelligibility, but we'll see it didn't quite do that. And then the free tempo I was testing was 60, 100, and 140 beats per minute, and I chose those because they are representative of a lot of music. And so if there is an effect, we can kind of see where it's happening roughly. I've also got one control masker, so that was speech shaped noise, so that doesn't vary with tempo and it doesn't vary musically at all. And then I've got, I'm using the R-spin speech corpus that's got high and low predictability sentences, and again that gives me another factor that I can test. But again, as we'll see, that was maybe a bit of a mistake. So in terms of the results, this is a bit messy. So on the left-hand side here, I've got my box plots. So, and I should also point out as well, the first time I ran the experiment, I had 22 people, got the data, was looking at it and thinking something doesn't quite look right. And then when I double checked, I realized I didn't have the same number of conditions for the same number of trials, sorry, for each condition. So I had to repeat the experiment again and only managed to get 13 people. So statistically speaking, this isn't powerful enough really, but this is the results anyway. And what we see, so anything with these red lines here, that's distinguishing the music. anything with the green lines, it's distinguishing the tempi within each piece of music. And then you've got on the left-hand side these low predictability sentences, and on the right-hand side the high predictability sentences. And what you'll see straight away is with these high predictability sentences, I've got a ceiling effect. So in other words, people are getting, like this one here, for example, where people are getting 100% for all the trials that I did. And then just looking at the statistical analysis, again, we can see over on this side here, you've got the high predictability sentences are kind of a bit too predictable in a way. And that might be to do also with the signal to noise ratio that I set up, but then that goes back to the glimpse proportion that I set everything to start with. So to have the same glimpse proportion, you have to have different signal to noise ratios for everything. And I guess it wasn't a high enough ratio to be able to differentiate between that. So then what I did next, I put all the scores for the high and low predictability sentences together, and I got a weekly significant result for the percussiveness, in other words, the music I've used. And it's mostly for this M2, so in other words, this solo cello. And again, I need to do some more analysis on this, some non-parametric analysis. But why is it that we are getting this result for the cello? Like, I would have expected that the M4, which had like thrown in, like the drums and everything, would have had a detrimental effect on speech intelligibility, and it's kind of been the opposite way around. It's the more sparse version. So I can kind of hypothesize about why that might be. And like I say, we've got a choice of music in there as well. So could it be that because it's sparse, it's giving greater glimpsing, even if I've set the signal to noise ratio such that it should be kind of equal glimpsing for all of them? But it could be that that higher signal to noise ratio is making it being perceived as being louder, and so that's having, people don't like that basically. Or could it be that the cello is within the same bandwidth as speech, and it's a narrow bandwidth as well compared to speech, so therefore it's also more salient? And also, could it be the fact that that particular cello music was quite repetitive, I guess, and played with quite high attack, whereas when it was in with the other instruments, it wasn't quite so repetitive. And so I guess I can kind of relate this back to literature review that I've been doing. So you've got auditory scene analysis from Bregman, principles of Gestalt psychology from Kafka, and the sequential grouping from Plack. So what they're basically saying is if something is perceived as being not with the same sound source, it's basically segregated. And so what I think is happening is that the cello is being segregated by the mind, and so therefore it's being more salient. But obviously I would need to do some more tests to try and prove that. And in terms of solution then for broadcast audio, you've got object-based audio. So in other words, you are broadcasting the audio stems and the metadata to the users rather than the finished mix, and then you've got a renderer at the user end, which is putting stuff together again. So you could say, for example, if you detect a solo instrument like a cello, you can maybe add more instrumentation to it. Or if people decide they don't like that piece of music, they could change the piece of music that they've got under a program. So that would be the solution. So in terms of this part one of the percussiveness and tempo, so we've looked at complaints about background music, looked at BBC directives about the background music, how I did objective evaluation using Jan's glimpse proportion model, and how I had to set the glimpse proportion the same, so therefore the signal to noise ratios are different for each music and piece of speech. Subjective evaluation, which was the listening experiments with a strong effect of sentence predictability and a weak effect of music. Potential reasons and the possible explanations. So that's kind of the end of part one. And then part two, which I think Sabina will like because it's environmental acoustics. So this is the stuff I did in the US then, and it's looking at volcano and geyser monitoring to track Santa sleigh. And again, if you are tweeting or not tweeting, you can have team enviro-acoustics or team infrasound. So your mission, should you choose to accept it, is to track Santa sleigh. But we have a bit of competition from ATS. So they've got SLADAR, as they're calling it, and they're doing a little test flight. So if you want to go and have a look at it, the website's on there. You can just take a screenshot of it and have a go. But we don't want to use SLADAR. We want to do our own thing. So could we use media device orchestration, but kind of in reverse? So in other words, rather than using it to play back your audio, could you use the microphones on your devices basically to act as an ad hoc array, is what I'm proposing. So how does it work exactly, or what's the background of this? So the stuff I was doing in the US, I was particularly interested in infrasound, so it's kind of the opposite of the psychoacoustics. So psychoacoustics, I'm looking at the speech bands, which are kind of between 20 to 20,000 hertz. For the environmental stuff, I'm looking at infrasounds, that's below 20 hertz basically, so below our human level of hearing. So it's low frequency, long wavelength, and it propagates over long distances basically. So that's quite nice because it means that you can use it to complement seismo-acoustic monitoring, and in particular it's used by I forgot the name of the organisation. That's like something like the CBTO. So they basically monitor any clandestine nuclear testing from North Korea or other places. Is what they're looking at. And then you can also use it for monitoring volcano eruptions as well. Or I should say explosive eruptions rather than effusive ones. So effusive ones are just where you've got like a lava flow like in Hawaii somewhere. Explosive ones are these nice big ones. And this image here, this is Bogoslov volcano in Alaska. This was an eruption that happened last year. And this plume is from satellite. So this is 40,000 feet, which I believe is roughly about 12 kilometers high. So it's quite a big eruption. There was kind of water interacting with, and that's what was going on there. And this is the reason why infrasound is so useful for volcano observatories, and particularly in Alaska, where it's difficult to get seismometers out and to kind of get them maintained as well. But they're quite busy commercial air routes, and so if a volcano is erupting, you need to be able to detect it and get a signal then to what's called the Volcano Ash Advisory Centre. They then notify the airlines and the pilots. There's like a thing in the cockpit which comes up with a message saying there's a volcano eruption in this area, you need to either avoid it or fly higher. So the planes basically aren't flying through it. So it's good also for detecting in poor quality conditions. So for example, at night time, or if the weather's bad, if it's raining or whatever, if you can't get satellite observations, it's really useful having the infrasound detection, because you'll only get the infrasound once something is erupting or exploding. So in other words, you've got a perturbation of the air. So again, that's why it's also good to go alongside the seismo-acoustics. Seismo-acoustics can say, okay, we can kind of see something might happen, or we can see this ground tremor, but we're not sure if something's actually erupted or not, whereas the infrasound and the aero-acoustics confirms that something's happened. The fact it's got long wavelengths as well means you can put the sensors a bit further away, so they're less likely to get damaged. But the only disadvantage, or the two disadvantages actually, is wind noise, which falls within our infrasound frequencies. That's below 0.1 hertz. And the cost of the high-grade sensors as well, and in particular for volcano observatories in places like South America or Vanuatu, for example, which is having quite big explosive eruptions right now as well. They can't really afford these sensors, but they'd be really useful to have. So the group that I was with in the US, we were looking in particular, or our objective in particular, was to try and develop low-cost sensor arrays that could be made easily, put together easily, kind of easily maintained or replaced as well. And so as well as the sensors as well, we're also looking at casing. So we're looking at 3D printing different cases and tried out different things with that. And you have to account for things like weather and animals trying to chew through stuff and all kinds of wind noise as well. You're looking also at the recording and transmission of data. So I wasn't involved in that side. That was something that happened after I left the US. But the guy who was the principal investigator of that particular project, when he went back to South America, they used mobile phones as to kind of transmit the data back to the volcano observatory, and they're testing that out, amongst other things. And like I said, the maintenance. So the two sensors that we tested, you've got these ECMs, which are basically the microphones in your mobile phone. They're low cost, so in the US they cost less than $1 per sensor, which is dirt cheap. And they've got good signal to noise ratio, but the downside is they have this low frequency roll off in these 1 to 5 hertz frequencies, which is not great if your signal of interest is in that frequency band. But it is adequate for detecting events at least. And then you have these MEMS transducers. They're slightly more expensive, but only by like $1 or $2, so the equivalent of like £2 maybe. And you put like a little tube over one of them, and again you kind of thread it through. Has good linear dynamic range, and it's got a good flat response as well for the frequencies of interest. And this one is better for modelling waveforms. So I'm not going to talk about this particular one today, but if you are interested, some of the other research I did with the geysers at Yellowstone were using these MEMS, and I've got some nice posters if anyone wants to see them at any point, where it shows some nice waveform analysis and characteristic waveforms and so on. So I'm just going to stick with these ECMs today. So to test them, we went to Yellowstone National Park, which was a 7-hour drive from where we're based. And we're using Yellowstone for the geysers because although they don't have ash in them like volcanoes, they erupt quite frequently. You can get quite close to them, you can see what's going on, you can video them. It's nice easy access. So you can literally, if you get permission from the national park, you can just go deploy your instruments, leave them for a few weeks, and then come back again. So it's dead easy. And we were specifically in the lower geyser basins. So this particular geyser here is called Great Fountain Geyser. And again, part of the research I was doing was at that geyser specifically. So that erupts twice a day, and you can just sit there with your beer by the roadside and just watch it going off. It's quite good fun. So this is a digital elevation model. So this just shows we had 3 arrays of 8 sensors each. So this is, oops, that's the lower Geyser basin, and then these are just the array configurations. So in the middle of each of these 3 arrays, you have one of those MEMS, and then all these other ones were the ECM sensors. And also in the middle, you have a data logger as well. So we weren't transmitting the data live, we were recording it and then going back a couple of weeks later and just going to collect it. And so you've got, here's someone setting up the sensors. And we left it for 2 weeks. And the other thing I should point out as well, so the distances, we measured out these distances and these azimuths. So these distances were 15 meters from the center, these ones were 30 meters, and that's just to kind of get a range of distances. So when you've got the waveforms coming in, or sorry, you've got the plane waves coming in, you can look at different arrival times at each station. So this is the bit I'm a little bit fuzzy about, so I have to apologise. I've had to nick this from my friend Brian Tavish's master's degree. So some of the things that we had to do once you get the data, so the data basically comes up as voltage differences, which you then have to convert to Pascal, so pressure in other words, and then you apply your bandpass filtering, so that's just filtering out mostly wind and also what they call earth tides. So earth tides are, as the Earth's rotating around, you've got the gravitational pull of the moon, which is causing like a bulge at the equator basically, and that's causing a diurnal or daily earth tide, sorry, so you have to filter that out. Then you look at the arrival times of the signals at each sensor in each array. You look at the cross correlation to determine what the coherent signals are, calculate your slowness vectors, and then you create semblance plots. So this here is your slowness grid, and I'll explain in a moment how that works then to create these semblance plots. So you'll have to apologise for this horrible looking slide. I was trying not to use too many equations, but I'll just explain it anyway. So first of all, you're going to calculate your apparent velocity. So like I say, at each station or each of these sensors, you have an arrival time that this plane wave is arriving at. So you can compare between, for example, number 6 and number 1, what's the difference in the arrival times to work out your travel time between the 2 of the plane wave. And then obviously, you know the horizontal distance between these 2 sensors as well, because you've carefully measured out these distances here and these azimuths, so you can work out by trigonometry if you've done it correctly. So then you get your apparent velocity or your reserved move outs. You're then going to calculate your adiabatic sound velocity in air, and there's another equation I haven't put on here because I don't want to put too many on here. But what we're saying is if your calculated VA is bigger than your calculated C, that means that the acoustic source is above horizontal. So in other words, it's coming from somewhere above sensors. If this VA is roughly equivalent to infinity, that means that the sound source is located directly overhead. So this we can apply to Santa's tracking of a sleigh. And likewise, you can also predict this as well from this TIJ as well. So then once you've got your VA, you're then going to look at your horizontal slowness, which is the inversion of this. And then from that, you can then work out your slowness vectors, which are all of these. In other words, this is your east-west slowness, this is your north-south slowness vector, and then this is your back azimuths. In other words, if you were at this sensor here and you're looking back to where the source of the signal is coming from. So you calculate it for all of these azimuths, I don't know what you call the plural, for like 360 degrees basically. And then you can also calculate this elevation angle of plane wave. So that's the only equations I'm going to put on these slides. You don't have to worry about them anymore. So basically, these plots here, you've got here, from this point here going around here is 0 to 360 degrees. So that is on the horizontal plane looking around. And then going from the inside to the out, so from the inside you've got 90 degrees and then 0 degrees. So that's to do with that elevation angle basically. So if you would have a semblance plot that plots somewhere in the middle here, you would then expect the sound source to be coming from vertically overhead, because basically that sound source is going to arrive at all the sensors at roughly the same time. If you got it on the outside here, that means it's a completely horizontal sound source. So in other words, your sound source is going to be arriving at different times at each sensor. So that's kind of the theory behind these semblance plots or slowness grids. And what you're looking at is, so semblance is just describing the strength of the signal. So you're going to take your slowness vectors, and then for each point on this grid, it's going to work out this variance basically. So if you're doing it in the time domain, this is it just in words, and if you're doing it in the frequency domain, you've got this equation here that you can use as well. And then what you end up with are these pretty plots here. So what I'm looking at here, this is roughly looking at distance. So 0, 0 is where we've got this Great Fountain geysers located around here. And then these are the locations of the 3 different arrays of 8 sensors relative to Great Fountain geyser. And we've got other geysers marked on here as well. So you're looking at the semblance plot for different time frames and different times. So this is one particular time which I took on this date and at this time for around a 30-second frame. And you're looking at the semblance plots from the point of view of each of these 3 arrays. So what this is telling me straight away is that this is a sound source that's coming from the horizontal, it's not coming from the vertical plane at all. And then if you look at the back azimuths, in other words, you're looking at the point of view from your array, and you're looking back at where the source is coming from. You can triangulate where the sound source is, and in this case, you can see it's coming from Great Fountain geyser. They're all crossing over quite nicely. And then just one more example. So this one was at a different time. You've got slightly different patterns again. So what this is indicating and what this is indicating is that there's more than one geyser erupting at any one point in time. And what I think as well, because you've got this one is going off in this direction here, but these 2 are looking in that direction. So it's possible that these ones are more than, possibly more than about 2 kilometers away, which is rough. I think the range of these sensors is probably up to about 3 kilometers maybe in terms of sensing what's going on. So you've got these 2 looking over here somewhere off the map at some geyser going off, and this one's looking over here, and it's looking over here somewhere. So like I say, you can just do these time frames and then look at what's erupting when. So in terms of for Santa then, I had to reconstruct this. So when we were at Yellowstone, there was one evening we were out camping by the fire, and we suddenly saw what are called bolides. So in other words, these shooting stars, which I thought quite cool. And we thought, we wonder if we can see that in the infrasound signal, like does that generate infrasound? And it turns out it did. And I've had to reconstruct this, but this is what it would have looked like. So as you've got the bullseye is in the middle, which would indicate you've got some kind of vertical sound source rather than horizontal. And if I was relating this to Santa Claus, then you would expect it to be kind of roughly in the middle like this again, but as Santa comes into land, it's going to go towards the outside with time. So that's what you'd expect. So can we use these, if you can use these ECMs, so in other words, the microphones in your mobile phone, which are good at detecting acoustic signals, could you then use it in some kind of like reverse media device orchestration then as a kind of ad hoc array sensor, or sensor array rather, to track Santa's sleigh? You can make your own mind up about that. But I just thought it was a neat idea anyway. So from this particular half of the talk then, I've been talking about infrasounds, how it's good for detecting explosions and eruptions, how I tested low-cost arrays at Yellowstone, with the microphones from your mobile phone are good just for detecting, and then these MEMS, these other sensors are better for capturing the whole waveform. You can create semblance plots and back azimuth plots then to analyse events going off with respect to time. So in other words, if you also want to apply that to Santa, then with respect to time, you can try and track where Santa's going. And we could maybe use like a media device orchestration in reverse to track Santa's sleigh. So if you do want to see anything else, this is some of the other stuff I was doing. So like I say, I looked at 3 particular geysers. So this one here is Sawmill Geyser, which is kind of a fun little geyser, which is no longer erupting, unfortunately. But it was quite fun. So there's 2 sensors there, and you can see from the cross correlation, actually, like these, just from the time series, even you can see these cross over quite nicely. You've got a fairly periodic signal, and so we're able to generate this nice characteristic waveform, which is going down and then up. So what we think with this particular geyser is happening is, with other geysers, you've got gas bubbles coming up and then exploding outwards. With this particular one, because we think the top of the geyser is quite shallow, so we think as this gas bubble is coming up to the surface, it's then being cooled very quickly at the surface. So it's imploding rather than exploding first. And then obviously it's got to go the other way, so then it explodes. So hence you get this, you get the downward signal first and then the upward signal. We had Great Fountain Geyser again. So that particular geyser, we were looking at trying to quantify the bubble burst. So we had video looking at it as well. And we're trying to, if you say that that particular geyser is like an isotropically radiating sound source, so it's radiating the same in all directions at the same time, you can kind of say, okay, you've got this bubble of gases expanding outwards once it reaches the surface. So we're using the waveforms to try and do that for Great Fountain Geyser. And then we also had, this was from Lone Star Geyser, so this is what's called a cone type geyser, sorry, get this right. So the other 2 are fountain type geysers, this is a cone type geyser. So it's a bit like Old Faithful, it's got a cone that's shaped. has a completely different behaviour. So it just starts with this general like water overflowing at the surface, and then it transforms into this steam jetting phase. So again, you can kind of see there's an increased amplitude, and there's also a change in the frequency response as well. So that's what we're looking at there. Also looked at volcanoes. So went to, this is Sakurajima volcano in Japan, where we had, there was a volcano conference. We also had a workshop there as well, so we were able to put some sensors out. And this particular volcano is kind of interesting because it goes quiet just before it erupts. And then obviously you get lots of infrasound from it. And so, and again, the people on the observatory are seeing this in the seismic signal. And what they're hypothesizing is that just before it erupts, you've got all these minerals that are percolating to the top of the cone, which is around here, and is mineralizing. So in other words, it's kind of filling a cap, and then the pressure builds up, and then it explodes. So we think that's why it's acoustically quiet before it erupts. And then the other people who are in the same research group as me over in the US, you've got people like Brian Terbush, who was looking at tracking what's called pyroclastic density currents. So these are kind of avalanches of hot volcanic gas and ash and rocks. And there was a particular volcano in Guatemala called Santiaguito, which actually has had quite a big eruption this year, quite devastating eruptions actually. But they were looking at trying to track the direction that these flows were going around the volcano to try and put in an early warning system, even if it's just a few seconds to give people time to get out, basically. And then you also had, there's Jake Anderson, who's just finished his PhD, so he's looking at shockwaves from Tungaragua volcano in Ecuador. So if you want to know anything more about those, then come see me. I can put you in touch with the relevant people. But otherwise, have a good Christmas.
In the first part of your talk, you were talking about an energy method that I haven't come across, energy evaluation method.
Oh, the energetic masking? Oh, hang on. You mean this one?
That one, yeah. Glimpse protocol. I haven't come across that concept at all. Could you explain that?
So I'll try to explain it. Like Jan is probably the best person to ask in all effect. So if you have both a speech signal and a noise signal, if, for example, you have something like white noise, it's just going to cover that speech signal, and you're not going to get any of that speech coming through at all, so you can't glimpse it. Whereas if you have something like music or something that is modulating, you might be able to catch some of that speech in between the masking noise. That's glimpsing. It's being able to hear parts of the speech when it's also with the noise.
All right. So is that then time-based, that at times the acoustic signal would, the music signal would basically allow a glimpse of the speech because there might be a lull in the music, or there might be different frequency range used.
Yeah, so if you have that, like you're saying, because it's also to do with frequency as well as, it's like a temporal spectral thing. So it could be that you mask at one kind of frequency band and your speech at another frequency band. It's more likely the speech is going to be the same band, but if it's not, that means it's less likely to be masking each other.
Mm-hmm.
And again, time-wise as well, like say if you've got the gaps in the music, you've got more glimpsing, so therefore you expect to have greater intelligibility because you're actually acoustically able to hear, audibly you're able to hear more of the signal to start with. Mm-hmm. Unless you've got other semantic cues like some kind of visual cue, in which case it doesn't really make much difference. Yeah.
What sort of frequency range infrasound were you considering?
For the geysers, so Great Fountain Geyser, I can't remember off the top of my head. I think below that 5 hertz range, but it's different for the different geysers. So, for example, Lone Star Geyser, the one that I said just has water coming out first, and then it has a steam jetting. It's kind of in the slightly higher infrasound range when it's the water, but then when you've got the steam jetting, it's going above the infrasound range, but it's still low frequency, so it's kind of roughly like 40 to 50 hertz maybe in the steam jetting.
Do you take into account things like Rayleigh waves in your array? Because you were just thinking about airborne sound.
Yeah.
Obviously, these things are ground-borne as well. Do you think the arrays would pick that up, or they go faster, don't they? I think Rayleigh, is that right?
Yeah. So I didn't look at Rayleigh waves just because the distances we've got our sensors to the sound source are relatively near. Like they're all within like about a kilometre or less. Okay. For long distance infrasound monitoring, so for example, like the nuclear testing stuff, yeah, you would be looking at that. And then obviously there's seasonal differences as well.
Right. Thank you.
So how do you get work group that works in these national parks. I wanted to go to that national park.
Yeah, I was lucky. So the guy who was the principal investigator for the US project, he got 5 years, well, not 5 years of funding. It was funding, sorry, for 5 different projects from the NSF. And so in his proposal, one of the proposals was to look at Yellowstone, just because it's quite easy to get to. Like, you just drive along the freeways for 7 hours and then you get to Yellowstone. But yeah, we had to ask for permission from the park as well. But when you explain what you're doing, and with infrasound, you're not sticking anything into the ground, you're not destabilizing anything. The only thing that they ask is that you try not to be seen too much by the public, because otherwise they think they can go off the boardwalks. And the other danger is bison as well. So we actually had an incident, bison at Yellowstone, yeah, because they're wild. We had an incident. We were setting up the sensors for one of the arrays, and the guy I was like setting up the sensors with suddenly said, "Put everything down and just back away very slowly." And there was a young bison headbutting a tree who wasn't very happy that we were in his patch, and so we just had to leave everything. And then the principal investigator went back later in the day and then managed to finish setting everything up. And luckily we left everything and nothing was chewed through or headbutted after that. But yeah, animals can be a bit of a concern as well. Anything else? Otherwise we can't go.
You're talking about mobile phone microphones. Are they able to pick up decent enough SMR at that lower frequency?
I don't know. Well, I mean, the thing is, we tested it and we were able to detect those events. So just for the detection, but for actually looking at the waveforms, it's not really that good. But you're able to get out enough coherence. You're able to get enough coherence from the signals to be able to say, okay, yeah, you're detecting something erupting over there.
So your sensor arrays were made up of mobile phones, were they?
They weren't the phones, they were the microphones from the phones. And basically we kind of mounted them on these.
So the method is, broadly speaking, relying on a few clusters of microphones.
Yeah, so you need at least 3 sensors in any array, basically. So if you have at least 3 sensors, you can triangulate.
But the way that you did it was you had clusters of sensors with, with some direction. Each cluster has a kind of direction to it, and then you're trying to
this one.
On that.
Yeah, so you've got these 3 clusters here, and then each cluster has 8 sensors within it and a data logger as well.
Yeah.
So, for example, if you've got a sound that's coming from this direction, it's going to hit this cluster of sensors before it hits this cluster, and then at some point this cluster. It's kind of like with our ears. If you've got something coming from that direction, it's going to hit this cluster first, and it's going to be louder in the cluster that's nearest. But then also within the clusters, because you want to know what is coherent and what's wind noise. So if you're getting a signal at all the sensors, then you can, and double check it obviously, you can say it's going to be coherent. Whereas if you're only going to get a few sensors, then it's more likely to be wind.
So presumably the spacing within your clusters, is that, does that have to be kind of low spatial aliasing type frequencies and things like that? Because it seems like you've got roughly around kind of wavelength type dimensions inside your clusters.
So it was more like this one is probably more representative. So you don't want them equally spaced, because then you would get aliasing. But so we're trying to, it's kind of a bit like an ad hoc array. You're not putting it in a specific configuration as such. It's more limited by how long is the cable that we've got. We can put them out. So like I say, these ones were 15 meters and these longer ones are 30 meters. But they're not, if you look at the way the angles you got these at, they're not evenly spaced in terms of angle. And again, it's so you can try and work out what's coherent noise and what isn't coherent noise.
You wouldn't be able to subdivide these arrays to see whether you can get some direction information from 3 subclusters of one array.
Yeah, you can do. There's another method which I haven't mentioned. So this method's used the Fisher statistics, and then there's another one which whose name I forget, but that's then looking at comparing between 2 sensors at a time within one array.
Thank you very much.
Okay.